Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 9. And today we're going to be talking about Section 9.2, hypothesis testing for the population mean when sigma is known. So remember in the last section, we kind of looked at the outline for this chapter. We're talking about two different types of hypothesis testing, testing about a mean and testing about a proportion. And then under testing about a mean, the method depends on whether sigma, the population standard deviation, is known or unknown. So in this section, we'll look at the case where sigma is known. And in the next section, we'll talk about what to do when sigma is unknown. So here are the steps for hypothesis testing when sigma is known. First of all, when can you do this? First of all, if your sample size is small, then your population must follow the normal distribution. Otherwise, if your sample size is large, the central limit theorem states that the sampling distribution follows the normal distribution, so there is no restriction on the population distribution. All right, so here's an example to kick things off. A new CFL bulb is claimed to have an average life that exceeds 8,000 hours. So if we want to test that claim, suppose that the average life of a random sample of 36 of the new bulbs is 8,120 hours, and assume that the population standard deviation for the life of CFL bulbs is known to be 500 hours. So on the next few slides, we'll show how to complete the steps for this test. First, we identify the null and the alternative hypotheses. We talked about that in the last section. So I find it easiest to talk about the alternative hypothesis first. Remember, that's written H sub 1. So the claim is that the bulb's life exceeds 8,000 hours. Exceeds means greater than. So that's automatically going to be our alternative hypothesis. Remember, the alternative hypothesis has to be either less than, greater than, or not equal to. And so automatically that's going to make the null hypothesis mu is less than or equal to 8,000 hours. So that's the status quo until somebody's made this claim. We have no reason to think that the average life of this bulb is greater than 8,000 hours. In the next step, we'll set a value for the significance level alpha. Now, in a statistics class, this value will usually be given. All right. In real life, you'll have to decide on it yourself. And remember, in the last section, we talked about setting the value of alpha depends on how bad would it be if a type 1 error happens. If you want a type 1 error to be really, really unlikely, you set the value of alpha lower. All right, so in this example, we'll use alpha equals 0.05. So there is a probability 0.05 of making a type 1 error. All right, next. Step 3 is to determine the appropriate critical values. So this is going to depend on two things. Number one, whether your test is left-tailed, right-tailed, or two-tailed. And since our alternative hypothesis has a greater than in it, that makes this a right-tailed test. And then the other thing that it depends on is the value of alpha, okay? So in the case where sigma is known, we're going to use a z-score for the critical value. The critical z-score identifies the rejection region for this one-tail test. And since this is a one-tail test, the entire area for alpha equals 0.05 is placed on the right side, specifically because it's a right-tail test. All right, so what you do to find your critical value is, since we're doing a right-tail test and alpha is 0.05, you shade the top 5% of the normal distribution and then figure out what z-score is the boundary between the top 5% and the bottom 95%. So using table A2, you can determine that that critical value is 1.645. If you look at your table A2, you'll see that value there. All right, so what's going to happen next is we're going to calculate a z-score for our collected sample. And if that z-score comes out to be greater than or equal to 1.645, we will reject our null hypothesis. Otherwise, we will not reject our null hypothesis. So the way that you calculate this test statistic is using this formula. So let's go over this notation. Z sub x bar stands for the Z test statistic. X bar, as usual, means the sample mean. And then mu sub H0 is the mean of the sampling distribution, assuming that the null hypothesis is true. So you can think of this as the population mean under the null hypothesis. So in this example, that would be 8,000. And then sigma, as usual, is the population standard deviation, and n is the sample size. So we know what all of these values are for this example. X bar is 8,120. Mu sub H0 is 8,000. Sigma divided by the square root of n is 500 divided by the square root of 36. This is definitely one of those times where you should try putting this into your calculator and make sure that you get the same answer that I do. In particular, let me point out that if you're going to put this expression all in at once, you need to put parentheses around this division on the bottom. Okay, if you don't put the parentheses there, you will probably get the wrong value. It should come out to about 1.44. All right, so now we will compare the z-test statistic with the critical z-score for a one-tail, or let's just say for an upper tail test, a right tail test. We will reject the null hypothesis if the z-test statistic is greater than the critical z-score. And in this case, 1.44 is not greater than 1.645, so we will not reject the null hypothesis. All right, now let's see. Yes, z sub x bar is not greater than z sub alpha, so we will not reject the null hypothesis. And this really right here is the way that I think about it. You're going to see a table coming up maybe on the next slide that's going to look very complicated. And I want you to feel free to ignore that table because I really think the easiest way to sort of remember this is not really to remember it at all. Just be able to draw the picture. And I mean, if your Z statistic comes out to be in the rejection region, then you reject. And if it doesn't, then you don't, okay? So you can see here the z-test statistic is not in the rejection region. That's why we're not rejecting the null hypothesis. Okay, so this is the table I was talking about. It looks very complicated. I do not recommend memorizing this. I just recommend draw the picture and then place your calculated test statistic in the picture, and you'll be able to see whether to reject or not. All right, and then the final step, this is very important, is to state the conclusion, not just reject the null hypothesis or do not reject the null hypothesis, but what does it mean in terms of this problem? And so you could say something like, according to our sample of 36 new CFL bulbs, there is not enough evidence to support the claim that the average life of these bulbs exceeds 8,000 hours. All right, another method for doing hypothesis testing is to use the p-value. The p-value is the probability of observing a sample mean at least as extreme as the one selected for the hypothesis test, assuming the null hypothesis is true. So what I like to say is, in a world where the null hypothesis is true, what is the probability of getting a sample this extreme? So extreme could mean one of three things, depending on whether your test is right-tailed, left-tailed, or two-tailed. If it's a right-tailed test, extreme means as high as the one that you got. If it's a left tail test, it means as low as. And if it's a two-tail test, it just means as different from. All right. What's the probability of observing a sample mean that is at least as different from the one we got? The p-value is sometimes referred to as the observed level of significance. And again, it provides another approach to deciding whether or not to reject the null hypothesis. All right, so we'll work this same example again with the CFL bulbs. The claim is that mu is greater than 8,000. Our sample result was that the sample mean was 8,120. Our sample size is 36. And sigma equals 500 was assumed known. The p-value represents the probability of obtaining a sample mean of 8,120 hours or greater. That's what we mean by as extreme as that in this example, if the true population mean is 8,000 hours. So the probability that X bar is greater than 8,120 is equal to the probability that Z is greater than this value, which is the Z-score of the 8,120 in your sampling distribution. And again, that Z-score comes out to 1.44. So using table A2, you find that the probability that Z is greater than 1.44 is 1 minus 0.9251, which comes out to 0.0749. So again, what that means is that if your population mean bulb life is 8,000 hours, then the probability of getting a sample of 36 bulbs with an average life of 8,120 is about 7.5%. 7.5% chance of that happening. We don't consider that to be too unusual because we set alpha to be 0.05. So we would say that this is not strong enough evidence that the mean is really greater than 8,000. All right, so here's a picture that illustrates what that looks like. Okay, the shaded area to the left, to the right of either X bar equals 8,120 or Z equals 1.44 is 0.0749, which is greater than the significance level 0.05. So this table shows you how to make your decision based on the p-value, and I'm going to show you in just a second here an easy way to remember this. If the p-value is greater than or equal to alpha, do not reject the null hypothesis. If the p-value is less than alpha, you do reject the null hypothesis. Or, as I like to say, I didn't make this up, if p is high, the null will fly. All right, that's how I translate this first line. If p is low, the null must go. All right, so if p is less than alpha, you reject the null hypothesis. If p is high, the null will fly. If p is low, the null must go. All right, I don't mind showing you how to find the p-value using Excel. I think it's just as easy to use table A2. You'll see in the next section, I am going to recommend using technology because you really don't have a choice when it comes to finding p-values in the next section. But in this section, you can just use table A2. So the way to do this in Excel is to use the command or the formula norm.s.dist. And the arguments for that function are first the z-score, and then just put the word true. All right, pretty much for a normal distribution, we will always put true there. Input the test statistic value for z, set cumulative equal to true to get the area to the left of the test statistic. So much like table A2, it's always going to give you an area to the left, which means you're going to have to remember for a right tail test to subtract that area from 1. Okay. All right, here's another example. The mean data use for smartphone users is claimed to be mu equals 1.8 gigabytes per month. Okay, the claim is that mu equals 1.8. Suppose data use is recorded for 49 randomly selected smartphone users, and the average use is found to be 1.86 gigabytes per month. Assume that the population standard deviation is known to be 0.20 gigabytes per month. Okay, so first we'll identify our null and alternative hypotheses. Because the original claim said that mu equals 1.8, that makes this a two-tailed test. The opposite of mu equals 1.8 is that mu does not equal 1.8. So that's going to be our alternative hypothesis. Mu does not equal 1.8. And then next we will set a value for the significance level. And again, in a statistics class, this will always be given. In this case, it's given to be alpha equals 0.05 again. Step 3, determine the appropriate critical values. Notice there are two of them this time because this is a two-tailed test. Sigma is known, so again, we're using a z-score. The critical z-score identifies the rejection region for this two-tailed test. Since this is a two-tailed test, we're going to split alpha equals 0.05 evenly into two tails, like you see in this picture. So the combined area of these two tails is 0.05. That means there's 0.025 in the lower tail and 0.025 in the upper tail. Using table A2, I would say the easiest thing to do would be to look for an area of 0.025. And you will actually find this exact value in table A2. It goes with a z-score of negative 1.96. So that means your two critical values are plus and minus 1.96. So the critical region, or the rejection region, would be z is less than negative 1.96 or z is greater than 1.96. So when I calculate my test statistic, if it comes out to be either down here or up here, I'm going to reject my null hypothesis. So calculating that test statistic using the same formula that we used before, 1.86 minus 1.8 divided by 0.2 over the square root of 49. Again, please try this on the calculator. Make sure you get the same answer. Should come out to about 2.10. Comparing that test statistic with the critical z-score, because 2.10 is greater than 1.96, in other words, it lands right about here in the rejection region, we will reject our null hypothesis. All right, like you see, I had backed up to the other picture, but this is showing you the same thing. So the conclusion could be stated, our sample of 49 smartphone users does provide sufficient evidence to reject the null hypothesis. We support the alternative hypothesis that average data use is not equal to 1.8 gigabytes per month. All right, and then to find the p-value for a two-tail test, it's the sum of two tail areas. Using the smartphone example, we found that the test statistic came out to be 2.10. So using table A2, the area to the left of negative 2.10 is 0.0179. Multiplying that area by 2, you get that the p-value is 0.0358. So again, what that means is that if the average data use really is 1.8 gigabytes per month, the probability of finding a sample that's this different from 1.8 is only 0.0358. There's only about a 3.5% chance of that happening. And since we've set our significance level to be 0.05, we say the more likely explanation is that the true population mean is not 1.8. And again, you can use the norm.s.dist function on Excel. If you put -2.1 as your z value, you'll get the 0.0179. You just have to remember, because it's a two-tailed test, multiply that value by 2. So you get your p-value is 0.0358. And, oh, one more thing, changing alpha changes the critical z-score in the hypothesis test, which in turn changes the rejection region in the sampling distribution. So this table here is something that you might want to put on your cheat sheet, you know, whatever notes that you look at while you're doing homework or taking an exam. These are the most common critical z-scores. Usually alpha will be one of these values. Occasionally it's something else, but not usually. And so this table gives you the critical z-score, both in the case where it's a one-tail test and in the case where it's a two-tail test. So just one thing I want to add to this is that if it's a two-tail test, it would be both the positive and the negative one of these values. But if it is a one-tail test, it would only be the positive or the negative, depending on whether it's a right-tail test or a two-tail test. So maybe I'll do that with a text box. Let me turn that, do this. Let's see, where can I put this? Maybe I'll put it right here. No, that's not good. Let's put it here. Okay, positive for right tail test, negative for left tail test. Okay, and then of course, if it's a two-tail test, it would be both. All right, just finding my mouse here. It's always hard to find, especially after I've been using a text box. Here we go. All right, and that is going to do it for section 9.2. So we'll see you next time.